The one thing that we can look into together a bit more precisely is the second result, which I think is more interesting. So again, we need that assumption of a separable metric space, which says that if we sample a data set that's large enough, we can get really close to pretty much any point that we might wish to evaluate. And we're going to say that P of x given y equals 0 and P of x given y equal 1, which are the distribution of the feature vectors given the two classes that we have here, are such that with probability 1, x is either a continuity point of P of x given y equals 0 and P of x given y equal 1, or a point of non-zero probability measure. Again, these are technical assumptions which are there to say that if you look at the point x that you're trying to assign a label to based on your classifier, that point x cannot be an outlier. This is really what that assumption is here for. It's telling you that somehow that point x you can approximate with other points usually. Understand that it's necessary in the following reason. Let's say that you're trying to classify cats and dogs, but there is a specific type of cat that is unlike anything else, and that specific class of cat is so weird that you cannot approach it with other cats. There is no other cat that looks like it. Then the problem you would face is that even though you might have a good classifier overall, you will never be able to approximate that weird cat really well because you can never get a cat that is maybe a little less weird and somewhere between the regular cats and that weird cat. These assumptions are nothing but the formalization of these ideas. And then as n goes to infinity, so as you get a larger and larger data set, what happens is you can show the following weird thing. The risk of the base classifier is less than the risk of the nearest neighbor classifier. Not surprising, because by definition, the base classifier is constructed to minimize the risk. But the risk of the nearest neighbor classifier, and we're looking at the one nearest neighbor classifier here, is upper bounded by 2 times the risk of the base classifier times 1 minus the risk of the base classifier. Now, if you remember that here, given that I'm using binary losses, my risk is always between 0 and 1. What this means is that you can further bound this simply by 2 times the risk of the base classifier. And what this means is that as n gets large, you are guaranteed that something as simple as your one nearest neighbor classifier will incur a risk which is no more than twice the base risk. So if you think about the base risk being small, then 2 times something small is still small. So that result here is telling you that the nearest neighbor classifier is actually a pretty good classifier as n gets large. So it might be surprising in the sense that, well, if we know that all we have to do is the nearest neighbor classifier, why the hell bother with anything else? Well, the reason is because there are a lot of assumptions behind that reasoning, some of which are hard to meet in practice, the main one being n going to infinity. Very often, what you have is you have a fixed data set, and it might be very costly to get more points. Therefore, the performance of your nearest neighbor classifier might be what it is. It might not be that good. It only gets good as n goes to infinity. So we're going to try to establish that result together, in part because it's an exercise in probability, applied probability. And for simplicity, I will not discuss the specific case where x is a continuity point of the conditional probabilities. I will only address the case where x is a point of non-zero probability, just because it's simpler. And the full details are in my lecture notes. And again, it's mostly here for reference. I want to reemphasize that my goal is to give you a sense for what people worry about when they do research in that field. So let's prove part of the theorem together. Everything else will be in the notes. So proof again. So we're going to assume, as I mentioned before, that we only look at the situation where x is a point of non-zero probability. So we're going to assume that x star, I'm going to call it x star to distinguish it, is a point of non-zero probability. Okay, so what that means is it means that the probability of generating the point x star in your data set, or as an example, is equal to some value p, which is strictly positive. Then what it tells us is it tells us that if you look at the probability that x star is not equal to its nearest neighbor in your data set, subscript, I'm claiming that that probability is 1 minus p to the power n, and therefore it goes to 0 as n goes to infinity. So again, what is the reasoning here? Because I know in that setting that with probability p, I can generate the specific point x star. It's like me saying there is a picture of a cat that you will generate with some probability. Then intuitively, I hope you agree with me that as the size of your data set gets larger and larger, the probability of not generating the point x star is 1 minus p to the n. Why? Because you generate every point of your data set of size n, id, according to a distribution that gets x star with probability p. So the probability of not getting x star is 1 minus p to the n, which goes to 0 as n goes to infinity. So it means that eventually, as n gets larger, your data set will contain the point x star. So when that's the case, what's happening? So as n gets large, if you x star belongs to the dataset D that you generate, so that if you look at the nearest neighbor of x star, it is actually x star itself because it is in the dataset. And then in that specific case, if you evaluate the risk condition on x star and its nearest neighbor in the dataset, it is actually nothing but the risk evaluated at x star and x star because x star belongs to the dataset. And this, according to the expression that I gave you earlier, is going to be the sum over k. So in that case here, I'm looking at the binary k, so sum for k in 0, 1 of eta k of x star times 1 minus eta k of x star. This simplifies a little bit further. You can write it as eta 0 of x star times 1 minus eta 0 of x star plus eta 1 of x star times 1 minus eta 1 of x star. But the last observation that you can make is that eta 1 of x star, what is it? That's the probability that y given x is equal to 1 given x star. Because things are binary, this is just 1 minus the probability of y given x of 0 given x star. And so that is actually 1 minus eta 0 of x star. And similarly, the term 1 minus eta 1 of x star, you can show is equal to eta 0 of x star. And so putting everything together, you will find that this is 2 times eta 0 of x star times 1 minus eta 0 of x star. Okay, so that expression simplifies quite a bit. In the case where x is a continuity point of this conditional distribution and not just a point of non-zero probability, one can argue that the same would be true. Now, the last thing that we have to establish is that indeed we do get a good bound for the risk of the nearest neighbor classifier. And so for that, I need to go back to the definition of the risk of the nearest neighbor classifier. And the other thing I'm going to do is I'm going to rewrite the base risk 2 in such a way that I can do a comparison effectively. So just as a note, in that specific case here, the base risk evaluated at a specific point x star, okay, so which is by definition, okay, this is the expected value over, since we're fixing x, over y given x, the way we generate the label of the indicator function, that HB, the base classifier of x star, is, so let me think for a second, is not equal to y. Now, because here we have only two classes, this condition here is the same thing as the expected value over y given x, that the minimum, as opposed to the maximum, of the eta k's, so the minimum, giving a step. So it's an indicator function that the argmin over k, which belongs to 0, 1 here, of the eta k of x star specifically is equal to y. Okay, so the reason I'm not putting the argmax, because the definition we established before is the argmax not equal to y, because it's a binary classification problem. If the argmin of eta k is equal to y, it means I'm making an error, which you can show is the minimum of k belonging to 0, 1 of eta k evaluated at x star. And because you only have two values, it's either eta 0 of x star or eta 1, and eta 1 is 1 minus eta 0, so this is nothing but the minimum of eta 0 of x star, 1 minus eta 0 of x star. Okay, so that's my expression for my base risk. In that specific case, I just rewrote it in a slightly different way. So now we are ready to compare it to our base. Sorry. Now I need to do one more thing. I need to compute my one more thing. I need to observe that if I compute RB of x star times 1 minus RB of x star, because if RB of x star is eta 0, 1 minus RB of x star would be 1 minus eta 0, and vice versa, this is actually always equal to eta 0 of x star times 1 minus eta 0 of x star. So let me box this. And you see that that expression here is half of what we established here earlier. So what have we established? Take a step back. We have proved, at least in a very specific case, that if you take the limit as n goes to infinity of the risk evaluated between x star, any point x star, and its nearest neighbor, x star, as n goes to infinity, it is equal to 2 times the base risk at x star times 1 minus the base risk at x star. That's what we established in the previous slide. So now what remains to be done is to understand exactly what's happening when we now average over the choice of x star. Okay, because remember, the risk here is conditioned on a specific point, but my true risk is evaluated based on the distribution that I have for my unseen points. And so what I need to evaluate is I need to evaluate the limit as n goes to infinity of the expected value over x star and over the dataset D, specifically, of the risk of x star and x, nearest neighbor of x star, in the dataset. So we have a limit, we have an expectation, we'd like to happily flip the order. In general, you have to be careful. Here the risk is bounded, so we can happily do that. And it can be justified using the dominated convergence theorem, but it turns out that you can write it as expected value over x star, my dataset D, of the limit as n goes to infinity of R of x star, x nearest neighbor of x star. And conveniently, this is exactly what we evaluated just a second ago. So this is nothing but the expected value over x star over D. So I guess it will go away actually, because we proved that as n goes to infinity, the nearest neighbor of x star becomes x star with probability 1. So we have to evaluate the expected value over x star of the risk of x star evaluated with x star. Okay, we're almost there. So now, if you look at the expected value of the risk evaluated at x star and x star, and the expected value is the x star that I generate. What can I say about this? Well, according to the calculation I've done, this is twice the expected value over x star of the base risk because of the expression star that I have over here. Expected value of RB of x star 1 minus RB of x star. And what I would like to prove is that that expression is actually less than twice the base risk times 1 minus the base risk. So one has to be a little bit careful when we write this because we have to distribute the expectation over two terms that form a product. So I have to be slightly careful with how I develop this. And the way I'm going to do it is therefore as follows. I'm going to expand things to write this as 2 times what? There is a first term, which is the expected value over x star of RB of x star. No questions? Good. Minus the expected value over x star. Now RB of x star multiplies itself, so I get RB of x star squared. Now this expression might look a little bit funny, but there's one way that we can simplify it to make it look nicer. The way I'm going to do it is I'm going to introduce and subtract a term. I'm going to write that as 2 times the expected value over x star of RB of x star, to which I'm going to subtract the expected value of x star over x star of RB of x star squared. So what I square is the expectation itself. Now, of course, if I subtract it, it means I have to add it. So I need to add again plus the expected value of x star, RB of x star squared. And then I have the last term that I have, which is minus the expected value of x star of RB of x star. This time the square is inside the expectation. And now what's happening here is if you look at that term right in the eyes, it is of the form the expected value of a random variable squared minus the expected value squared. And this is nothing but minus the variance of RB of x star. And this, by definition, a variance is a positive quantity, so a variance is negative, so this is a negative quantity. And therefore, we can upper bound this simply by the first term, and the expected value over x star of RB of x star is nothing but the base risk, and 1 minus the same square is 1 minus RB. And that therefore proves the theorem that we care about. So as you see, things do get rather technical and not completely straightforward, but at least in a simple case, we were able to establish that as n goes to infinity, you can bound the risk of your nearest neighbor classifier by twice the base risk times 1 minus the base risk.